Welcome to lecture number 24 of the course on high performance computing. We are looking at the idea of a pipeline processor and are currently trying to understand the different kinds of hazards that may have been taken into account in the design of the processor. The hazards are situations where instructions cannot proceed at the maximum throughput rate of the processor. Recall that pipeline processors try to get high performance by having the maximum possible throughput rate at which instructions are executed. So, we are currently looking at the problem of data hazards. Let me just remind you that we have looked at a few possible solutions to the data hazard problem. One of them was that the pipeline could be built to include pieces of hardware called interlocks that check for data hazards, and when a data hazard is detected, the hardware would cause the dependent instruction to be stalled. And what we mean by stalling an instruction is preventing it from proceeding through the pipeline as per schedule. Another possibility we saw was the idea of forwarding, and the idea here was if the result that the dependent instruction is awaiting is available, maybe not in the register file, but somewhere else in the processor, then if it can be provided through a short circuit path to the point where the dependent instruction requires it, then there may be no need for the delay of stalling the instruction. And we looked at a special case for load instructions called the load delay slot. Now, we are going to look at a fourth possibility, and that is the possibility of scheduling the instructions, in other words reordering the instructions so that the dependent instructions are far enough apart so that the hazardous situation is resolved. And the scheduling of instructions could either be done by the compiler, in other words before the program runs. In other words, if you looked at the executable file, the a.out, you would find the instructions in their rescheduled order, not the order which had the problem with the hazard. The alternative would be, and we will look at this only briefly, that the hardware could be designed, the pipeline processor hardware could be designed to do the rescheduling, the reordering of instructions dynamically. We will start by looking at the idea of static instruction scheduling. So, the idea here is that the instructions of the program could be reordered to eliminate the data hazards, and we realize that arbitrary reordering of instructions may not be safe, and that the reordering must be done in such a way that the meaning of the program is not changed. Okay, so if it is determined that two instructions are essentially independent of each other, then those two instructions could be interchanged, and that would form a basis for trying to do the reordering of instructions. Now, we will understand static instruction scheduling through an example, and here is a code example. Now, you will recognize the MIPS instructions in this code fragment. What I mean by a code fragment is that clearly this is not a complete program in itself, it is just an extract from a program, and we are looking at an extract of interest to us. So, you will notice that it starts with loading the contents of some memory location into register R3. Subsequently, the value in that register is incremented by 1, the result goes into R5. Then the same value is involved in an add instruction, R3 being the value I am referring to. After this, there is a load word instruction and another add instruction. Now, we first need to identify any problems with this piece of code in order to consider what kind of reorderings might be, reordering of instructions might be useful. Currently, if we look at this piece of code and we bear in mind that there is this concept of the load delay slot, we observe that there is potentially a problem as far as the value R3 being loaded and it being used in the immediately following instruction. So, we suspect that if this was a processor which used interlocks, then it would possibly have had to stall the add I instruction by 1 cycle. So, I have inserted that comment there, that in the absence of some form of rescheduling of this code, there would be the need for 1 cycle, a 1 cycle delay between the load word instruction going through the pipeline and the add I instruction going through the pipeline. Hence my notation of the need for 1 stall in between. Now, that is the primary problem with this piece of code. You will notice that there are others. For example, in the second load word instruction, which loads into register R13, the immediately following instruction once again uses R13 as a source operand. Therefore, there too there is a need to stall the pipeline or to stall the add instruction for at least 1 cycle before the value will safely be available in R13, in register R13, or before the value can be bypassed appropriately. So with this piece of code, then we have these two problems as marked by the two red arrows and the notation of one stall. Now the question is, if I wanted to reschedule the instructions, this is the existing order of the instructions, I need to try to do some reordering of the instructions in such a way that the problems disappear, or the need for these two stall cycles is removed. And I need to try to do this by changing the order of instructions. Now, in looking at the first two instructions, very clearly there was no question of interchanging them, because the second instruction uses R3, which is written by the first instruction. And we could look similarly at many of the instructions to determine which of them could be reordered. But let me just quickly cut through the analysis and point out that if I was to move the load word R13 instruction up from its location near the bottom of the program, it used to be over here, I have now moved it up there. What have I achieved? I have caused the need for the stall between the first load word instruction and the add I instruction to be eliminated. Now the load word instruction, which loads into R13, and the first instruction which reads into R3, and the add I instruction, which is the first instruction that uses the load value, are separated by one instruction, the load word R13 instruction. Hence, there is no need for that stall cycle. By the same token, I have separated the load word 13 instruction from the first instruction that uses the loaded value by at least two instructions. And therefore, I have eliminated the need for the second stall cycle. Therefore, this movement of the load word R13 instruction actually solves the problem. But prior to doing that, we do need to determine whether it is safe to interchange or to reorder these instructions in such a way that the load word R13 instruction moves from its location towards the end of this code fragment up to the location where I had moved it. So essentially, I need to determine that the load word R13 instruction is independent of the two instructions which it is now going to precede. And looking at these, for example, I look at the load word R13 instruction, I notice that this instruction uses R11 and modifies R13, whereas the add instruction uses R2 and R3. In other words, they have no registers in common. Further, I know that these two instructions have no side effects. They don't have any implicit operands like R31. And therefore, with some confidence, I can say that the load word instruction is independent of the add R2 instruction. I still have to check whether the load word R13 instruction is independent of the add I instruction. Once again, the same reasoning tells me that they are independent. The load word instruction uses registers R13 and R11. The add I instruction uses registers R5 and R3. They have nothing, they share no pieces of data. And therefore, I determined that, in fact, the load word R13 instruction can be moved to the location that I had specified safely. The meaning of the program will not be affected in any way. By doing this, I eliminate the need for the two stall cycles, and in effect, this sequence of instructions will run through the pipeline with each instruction immediately following the instruction before it in the code fragment. So this is a simple illustration of how, by just changing the order of instructions after having thought through the consequences carefully, the need for stalling instructions could be eliminated. And this is how static instruction scheduling could be done by a compiler to remove data hazards. We should note that the data hazards which existed in the pre-scheduled code cease to exist in the rescheduled code, and therefore we have successfully removed the data hazards. Okay, now the example that we just looked at assumed that the work was done by the compiler, and I had talked about the alternative where there could be processors which are designed so that the hardware does this rescheduling of instructions dynamically. I had suggested in the previous lecture that today such processors are not uncommon. I will just make a few comments about that, but prior to talking about the processors, I'd like to clarify a few kinds of data dependencies that the compiler or the hardware may have to check for. Now, the first kind of dependence between two instructions, data dependence between two instructions that we had seen, was of the kind where one of the instructions, or let's say the earlier instruction, generates a value in a register in this example, which is used by the subsequent instruction. And the problem now is that the second instruction is dependent on the first instruction for the value of R1. And this kind of dependence is known as a true dependence. There are other kinds of dependence, data dependence, that we did see. And the one example that we did see, for example, in the previous lecture, was the situation where the subtract instruction is writing or using R2 as destination, and the add instruction which precedes it uses the same register as its source. Now, there is no real danger as far as the execution of these instructions in this order is concerned, as far as we can see, because the add instruction will read R2 well before the subtract instruction updates register R2 in a normal pipeline. But we do need to note that there is a dependence between these instructions, in the sense that if I had thought of reordering these instructions, in other words putting the subtract instruction before the add instruction, then the meaning of the program would change, because if I put the subtract instruction before the add instruction, then the add instruction would receive the value of R2 which had been created by the subtract instruction, which was not the meaning of the original program. Hence, we must view this kind of a pair of instructions as also being dependent on each other, and this kind of dependence is known as an anti-dependence. Right. So, you can clearly see the difference between the two. In the true dependence, the first instruction in the pair generated a value which was read by the second instruction in the pair, whereas in the anti-dependence the opposite was true. The first instruction of the pair used a value, a register, which was updated by the second instruction in the pair. Now, there is a third kind of data dependence that hardware may have to be aware of and check for, if one is assuming that the hardware does the rescheduling of instructions, and that is something called the output dependence, as illustrated by this example. And here we notice that there are two instructions, both of which have the same destination register. And if we think about this, we realize that the consequence of reordering these two instructions would be that the add instruction would update R1 after the subtract instruction updated R1, which would change the meaning of the final value inside the register R1. So, the final value of R1 would change if I reordered these instructions, and hence the meaning of the program would change, and therefore, that would not be a legitimate reordering from the perspective of instruction scheduling. Therefore, in general, there are these three kinds of dependencies that the compiler or the hardware, depending on who is doing the reordering of instructions, would have to take into account. Now, when it comes to hardware to do the reordering of instructions, we are still talking about a pipeline processor, but I will sort of generalize the capabilities of the processor to give you a better perspective on what pipeline processors today might actually look like. In the kind of pipelining that we were discussing up to now, we talked about 5 pipeline stages: instruction fetch, instruction decode, execute, memory, and write back. And the assumption that we used was that there was no instruction scheduling, and therefore the instructions would go through the pipeline as specified by the program, sometimes benefiting from bypassing, sometimes having to be stalled, depending on the way that the data hazards are being handled. Now, let's talk a little bit about how things could change with dynamic instruction scheduling. Now, if there is dynamic instruction scheduling, there will still be a need to fetch and decode the instruction. Hence, we suspect that there would still be an instruction fetch stage in the pipeline of the dynamic instruction scheduling processor, and there would still be the need for instruction decode stage to decode the instruction. However, it may not be necessary, it may not be possible to actually do the fetching of all the operands within the instruction decode stage, and therefore that functionality may be removed from the instruction decode stage. So, I will just put a prime over the ID to indicate that this is different from the instruction decode stage that we had in the pipeline that we were discussing up to now. Recall that in the pipeline that we were discussing up to now, the instruction decode stage had hardware to do the decoding of the instruction and the fetching of the register operands. Now, if I am talking about a dynamic instruction scheduling, there may be the need for an instruction's operands to be fetched after waiting for the operand values to become available in the registers, and hence that particular functionality may not be present in the ID stage, hence the notation ID prime. Now, if the hardware is going to be built to dynamically schedule the instructions, that would imply that it is not proceeding, it is not allowing the instructions to proceed to the next stage in the pipeline in the order in which they were fetched and decoded, and hence there must be a pool of instructions or a piece of hardware memory within the processor where instructions that are under consideration for being scheduled next could be contained. Subsequently, all of those instructions one by one would execute, but during the time that they are being considered for being scheduled as the next instruction to execute, they would have to be remembered, and hence there would be some kind of a hardware data structure, some kind of a memory storage with associated logic within the processor, where instructions could be saved after they had been decoded for consideration for scheduling. And this kind of a structure in a pipeline would be referred to as an instruction window, or in some cases as an instruction queue, though it is not going to be treated as a first in first out queue clearly. If it was a first in first out queue, that would imply that the instructions enter the queue in some order and come out of the queue in the same order, which is clearly not the case here, because we are talking about dynamically scheduling the instructions in some different order. So basically the instructions get fetched, they get decoded without operands being fetched completely, and then they are put into this instruction queue, where the hardware of the dynamic instruction scheduling, which implements the dynamic instruction scheduling, determines which of the instructions should be allowed to execute next, and need not be the instruction which was first fetched and first decoded, but could be one of the later ones, as long as the meaning of the program does not change. So those considerations would have to be taken into account by the hardware that does the scheduling, and that would be the dynamic instruction scheduling component of the pipeline. Now, to just give you a different perspective on how the rest of the pipeline might be organized, and my discussion from this point on does not specifically relate to dynamic instruction scheduling, but is just to give you a more general perspective on what the rest of the pipeline might look like. We should note that when we talked about the simple pipeline, we had the execution of instruction, but we really had only one piece of hardware that was doing the execution. Specifically, there was an ALU, which was doing the execution of the instruction, and it was used for add instructions, it was used for subtract logical instructions, but it was also used for load word instructions to calculate the effective address, and further it was also used for branch instructions to calculate the branch target. However, we do know that even in our MIPS1 instruction set, there are instructions which cannot be executed by the ALU. For example, there could be floating point instructions. So we suspect that in addition to just the ALU, for the execution of instructions, there may be several pieces of hardware, each specialized to do different kinds of operations, and that therefore when thinking about the processor pipeline, it's not that thinking about the processor pipeline as just having an ALU is not realistic. Rather, we should think of a pipeline which has many different pieces of hardware for different functional capabilities as far as the instruction set is concerned. For example, if there are floating point instructions, there must be a piece of hardware that can add floating point values. Similarly, a piece of hardware that can multiply floating point values. Maybe another piece of hardware to do the division of floating point values. As far as the integers are concerned, there would need to be an integer ALU. There may also be the need for an integer multiplier. You may suspect that multiplication of integers is a little bit more complicated than addition of integers, and therefore there may be a separate piece of hardware to do that. Further, we could actually say that rather than having a separate memory stage, we could view the operations associated with the memory stage from our prior description of the pipeline as actually just being another functional requirement which could be met by another functional unit, which I label as the memory unit. So there could be a large number of such functional units. The number would depend on the nature of the instruction set and how much functionality could be built into each of the functional units. Subsequently, when an instruction completes, it would still have to write back. Therefore, we would suspect that there would be a write back stage. Now, the question that you will ask at this point is, how many stages are there in the pipeline that we have just drawn? And the answer is, we can clearly see that there is an IF stage, there is an ID stage, and there is a write back stage. But as far as the EX, what used to be the single EX stage is concerned, you notice that I have shown the different functional units as being of different lengths. And the suspicion that you may have had is that I am using different lengths because the amount of time to execute an operation through that functional unit may be more. For example, in the case of floating point multiplication than in the case of a single integer ALU, which is why the floating point multiplier unit itself is longer. So the consequence is that we may want to think about the functional units themselves as potentially being pipelined. So this floating point adder might have a 6-stage pipeline. It may be a pipeline floating point adder. The floating point multiplier may be an 8-stage or 7-stage multiplier. The integer ALU may be a 3-stage integer ALU, etc. So these functional units might themselves be pipelined, and therefore the number of cycles that it takes for an instruction to go through the pipeline might be 1 for IF, 1 for ID. The instruction might spend 3 or 4 cycles waiting in the instruction queue. Then it might spend 5 or 7 or 3 or 1 instruction or a cycle in the execution unit before spending 1 cycle in the write back unit. So the thing to note here is that by doing dynamic instruction scheduling, the order in which the instructions are fetched and decoded is not going to be the order in which they get executed. Right? So the hardware dynamically schedules instructions from the instruction window for execution on the functional units, and hence the instructions could execute in an order that is different from that specified by the program. In general, the reordering must be done safely. So the consequence of executing the instructions in this different order should not result in a different outcome of the program. So that checking for independence of instructions is important. But we should note that the order in which the instructions execute could be different from that specified by the program. And I mean, the result should be the same. Such processors are hence sometimes called out of order processors, in that they execute the instructions in an order that is different from that specified by the program. The order specified by the program is often referred to as the program order. But in the interests of eliminating data hazards or improving the performance of a particular program, the hardware might schedule the instructions to be executed in some other order, and such a processor would be called an out of order processor. Now I'll just go back to the previous slide and point out that the instructions would, in this particular scheme of things, it's conceivable that the instructions would be fetched in program order, which I'll write as in program order. The instructions would consequently be decoded in program order. Now they may be scheduled for execution out of program order, but there may be a requirement that they actually complete their write back in program order. And this is a common characteristic of many of the aggressively pipelined processors today. They are in order, in program order in their early stages. They finally finish instructions in program order. It is only in the intermediate stages that, in order to eliminate data hazards or to improve performance, that they handle instructions in a carefully checked different order. Hence the term that you may see in some of the literature or in sales literature that you read about an out of order processor. So much for instruction scheduling. Okay, now with this we have understood two kinds of pipeline problems. One was the structural hazard, one was the data hazard. We will next look at the third class of hazards, which I had called control hazards. And in the introduction I had mentioned that a control hazard is a hazard that arises due to control transfer instructions. Let's try and understand a control hazard once again through an example. Now let me just remind you from our basic hardware that we had derived how a conditional branch instruction gets handled through the pipeline. Remember that it gets fetched using the fetch hardware, it gets decoded using the decode hardware. Let me show you an example of a branch instruction. Branch if equal to 0 R1 target address. The target address is specified as a displacement from the program counter. So I'll write it in that form. So when this instruction is fetched, subsequently when it is decoded, during decode the instruction will be properly understood and the contents of its operand register, in other words R1, will be read from the register file. In the execute stage, two things have to be done. One is that its target address has to be calculated within the ALU, and secondly, the target address calculation within the ALU amounts to the calculation of using the displacement from the program counter value. And you'll recall that in the case of the MIPS1 instruction set, the calculation was PC plus 4 minus 8. In addition to that, the check of the condition must be done, whether the contents of register R1, which was read into one of the special purpose registers within the processor in the ID stage, is in fact equal to 0. So that is the condition checking, which also we assumed was done by hardware included in the EX stage of the pipeline. Subsequently, nothing of interest happens in the MEM stage, and in the write back stage the program counter value could be updated. So that's what happens during the execution in our pipeline processor of a conditional branch instruction. So let's look at that example more critically. So here's a similar instruction: branch if equal to 0, R3 out. So once again, I'm going to use the timeline. The branch if equal to 0 instruction goes to the pipeline as we have just described, the IF stage, ID stage, EX, nothing much of interest happening in the MEM stage, and finally updating of the program counter value possibly in the write back stage. Now from the discussion on the previous slide, you will remember that the important part in the pipeline where the activity of the branch instruction was reasoned out happened in the EX stage. That's where the target address was calculated and also where the condition was checked, whether the contents of R3 were equal to 0. Therefore, we know from that discussion that in our current scheme of the pipeline, the condition and the target are resolved or determined as far as this branch instruction is concerned by the end of the EX stage. Let me just go back to the previous slide to make sure that's what we had reasoned. By the end of the EX stage, the condition would have been evaluated and the target address would have been calculated. So that's all that I'm marking in this slide. It's by this point in time that the condition, in other words, is R3 equal to 0 or not, and the target, in other words, what's the actual address associated with out in terms of its PC relative addressing mode, are resolved by now. Therefore, the problem which arises as far as the pipeline is concerned is, let's suppose that this branch if equal to 0 instruction was fetched in what I'll call cycle number 1 and is decoded in cycle number 2, etc. So I'm just numbering the cycles. Now the question is, after the branch instruction has finished using the IF stage, we know that in the next cycle, when the branch instruction is using the ID stage, we want some other instruction to be fetched. But the problem that we have is we don't know which other instruction should be fetched. The question that arises is written here: should we be fetching the next instruction or should we be fetching from the target? In other words, will the branch be taken or not? And since we don't know the answer to that question, we don't really know, and therefore we suspect that what would have to happen is that the pipeline would have to stall for that cycle. In other words, the IF stage could not fetch any instruction because the branch instruction has actually not reached the stage of execution where we know which instruction has to be fetched. Therefore, we can't answer the question of whether we should fetch instruction I plus 1 or the instruction from the target of the branch. Hence, the need to stall the pipeline. Now the question is, that's what happened in cycle number 2, but in the next cycle, can't we fetch the correct instruction? Now unfortunately, the activity of fetching in the cycle number 3 would have to start in the IF stage at the beginning of the cycle. And from our understanding of what happens in the EX stage as far as the branch instruction is concerned, we realize that whether or not the branch is going to be taken and also what the target address is will be known only by the end of cycle number 3. Hence, even in the next cycle, we are not in a position where we can answer the question whether we should fetch instruction I plus 1 or from the target, and hence we'd actually have to stall this pipeline for one more cycle in which we have to push a bubble into the pipeline rather than a useful instruction starting through the pipeline. Now, what this boils down to is that the earliest that we would be able to fetch, the earliest that we would know which instruction we have to fetch next would be in cycle number 4. We would know whether the condition was true or false, and therefore whether we should fetch from the target address or from the fall through address. And hence this would be the situation as far as the control instruction like the branch if equal to 0 is concerned. Notice that the consequences are very bad from the performance viewpoint, in that after every conditional branch instruction like this, there would be the need to have 2 stall cycles. In other words, 2 cycles in which no instruction would complete later on down the pipeline. So this is actually an unfortunate observation, that associated with every branch instruction, there will be these 2 cycles after the branch instruction when basically a bubble would have to go through the pipeline, or in our current terminology we talk of this as 2 stall cycles, when we are uncertain in this case as to what instruction should in fact be fetched. And this is the control hazard problem. The problem that after every conditional branch instruction of this kind, there is a need to actually stall the pipeline for 2 cycles. It's a hazardous situation in that there is a performance loss. It's a hazardous situation in that if the pipeline is not built to do these 2 stall cycles, then incorrect program execution would result. Now, immediately the reaction of the computer architect would be, we have to find some way to reduce that number of 2 stall cycles. That's too heavy a price to pay for the execution of branch instructions in a pipeline. Remember that in the case of pipelining, we want to get the maximum rate of execution of instructions. We want to avoid situations where there is a stall, a cycle in which no instruction completes. Now, in analyzing what's happening in the case of the branch instruction, we realize that the bottleneck, the problem is arising because the 2 pieces of functionality as far as the branch instruction are concerned, in other words, evaluating the branch condition and computing the branch target address, are both happening in the EX stage. And that if we could find a way to do it earlier, then we could reduce the impact of the branch instruction on performance. So, as a very aggressive piece of hardware design, we might say we can try to reduce the branch stall effect by evaluating the branch condition earlier, in other words, in the ID stage, and computing the target address earlier, in fact in the same ID stage. And we need to think about this a little bit because it doesn't seem feasible. If you go back to the picture of the pipeline, we know that the checking of the condition and the evaluation of the branch target are happening in the EX stage. The suggestion now is that they could be done in the ID stage, but you'll notice that register R1 is read only in the ID stage. Now, if I did want to do the condition check and the target address calculation in the ID stage, at the very least I would need to have the hardware to check comparison with 0 inside the ID stage. In addition, I would need a simple ALU in the ID stage in order to do the target address calculation. Even this would not be adequate to solve the problem because we note that our assumption as far as the way the ID stage functions is that the reading of the source operand within the ID stage happens towards the end of the cycle. And therefore, if I wanted to take the result from the register, in other words R1, and compare it with 0, I would have to make the cycle time of the ID stage a little bit longer. So, in addition to whatever work it used to do, I now want to add the work of comparison with 0 and calculating the target address, which is going to mean making the cycle time a little bit longer. But if I am willing to accept these overheads, the overheads being a piece of hardware to compare with 0 inside the ID stage and an additional ALU, a simple ALU included inside the ID stage, along with a small time overhead of the cycle time becoming a little bit longer, then it turns out this becomes feasible. It is possible to reduce, it is possible to identify whether the condition of the branch is true or false in the ID stage, and it is possible to compute the target address inside the ID stage. And what would be the impact of this on the branch hazard, the control hazard? The answer is the number of stall cycles would then reduce to 1 cycle. Notice that if we go back to this diagram, we are now assuming that the condition and the target will be resolved by the end of the ID stage, which means that while I would still need this stall cycle, I would not need this stall cycle, and the correct instruction could correctly be fetched in cycle number 3, which means that there is only 1 stall cycle which is required. So, the number of stall cycles would then be reduced to 1. We still have 1 stall cycle, and ideally we would want to have a pipeline in which the control hazard is fully handled, in other words where there is potentially no stall cycles. So, we need some more ideas to understand how such pipelines might be designed. Now, I am going to talk about a few ideas which are sometimes used in processors for handling control hazards, essentially to remove that 1 stall cycle which we were left with at the end of the previous slide. Now, one idea which is sometimes used is to do something called static branch prediction. We have come across the word static and the word branch before, but the word prediction comes as a bit of a surprise because when you hear the word prediction, you assume that this means reasoning about the future. Predicting is to talk about something which has not yet happened. So, trying to talk about guessing what is going to happen. And that seems to be what is suggested here, that as far as the branches are concerned, try to guess what is going to happen as far as the branch is concerned. The word static we have seen before. We know that that means that this is some kind of activity which is going to primarily be done when the program is compiled statically, once and for all, which typically means when the program is compiled. And that is essentially what we are talking about here. So, putting all those terms together, static, branch and prediction, this is what we come up with, that this is an idea of the behavior of a branch instruction being predicted once before the program even starts executing. Right? And this is a rather curious notion, but if one could predict what the branch is going to do before the program starts executing, then conceivably one could set up the processor pipeline to use that information and successfully handle without the need for the stall cycles. Let's think about this in more detail. Okay, now one problem with prediction or guessing whether the branch, things about the branch, is that the guess may be wrong. And if the guess is wrong, then the program would behave incorrectly. And very clearly that is not acceptable. What I mean by incorrectly is the program would not execute as specified by the instructions within the program. So very clearly, since the guess about the branch could be wrong, the prediction could be wrong, the pipeline processor hardware must be built to detect a misprediction and then take appropriate corrective action so that the net result is that the program executes correctly. One cannot sacrifice correctness in the interest of performance. Just to remove the stall cycle, the control hazard stall cycle, one cannot build a processor that does not execute programs correctly. Therefore, this is the consequence. The pipeline processor hardware must be built to detect mispredictions and take appropriate corrective action. Let's look at a simple example of static branch prediction and understand this. Now, the example I am going to talk about is a static branch prediction policy called static not taken policy. And as the name suggests, the idea is to assume that branches are not taken. Right, so, basically what does it mean to assume that a branch is not taken? If I have a branch if equal to 0 R3 target, and I assume that it is not taken, then by default the instruction that is going to be executed next is going to be the next instruction in the program. And therefore, what that boils down to is building the hardware to automatically fetch from the next instruction, not from the target, but from the fall through path. So, that is the idea of the static not taken policy. Build the hardware to automatically fetch from the next instruction. In this slide, I am denoting this as PC plus 4. We may correct that, but essentially what we are talking about is the next instruction. Okay, now, what kind of corrective action could be taken? Now, the corrective action that could be taken is, we know that by the end of the ID stage, in other words, the branch instruction is fetched, and in the IF stage it itself is fetched. When it goes to the ID stage, some other instruction is going to be fetched, that which instruction is answered by this line. By the end of the second cycle, the ID stage contains the hardware to not only find out if the branch condition is true or false, but also what the target address is. Therefore, by the end of the ID stage, we know both whether the condition is false or not and what the target address is. Now, if it is found out that the condition had been wrongly predicted, in other words, that the branch is supposed to be taken, that the static prediction of not taken was wrong, then what will have to be done is the instruction will have to be negated, and the term which we use for that is to talk about it being squashed. So, the technical term squash basically means to cancel or annul the processing of that instruction. So, this is a hardware activity. So, the hardware makes this kind of a guess. If it finds out that the guess is wrong, then it has to undo the work that it has done by squashing the instruction. Let's just look at this with an example. So, here's our branch if equal to 0 R3 out instruction. Now, in cycle number 1, this instruction is fetched, and we know that in cycle number 2 it is decoded, but until cycle number 2 is over, we do not know what the next instruction that should be fetched is. Now, if we are using the static not taken branch prediction policy, then in cycle number 2, while the branch instruction is being decoded, we automatically fetch instruction I plus 1. The assumption here is that the branch if equal to 0 instruction is instruction I. So, we automatically fetch instruction I plus 1, in other words the next instruction in the program. Now, by the end of the ID stage, we know whether our guess of not taken was true or was correct or not. Now, let us suppose that the guess was correct and that the condition evaluates to false, in other words the branch is not taken. Then the fetch which we have done is correct, and the rest of the sequence of instructions goes to the pipeline normally. Therefore, if it turns out that our guess was correct, then we have actually avoided the stall cycle. So, there are no branch stall cycles, but this is not guaranteed to happen all the time, the condition always actually evaluating to false. So, we need to look at the other possibility. In the other possibility, as before, the instruction is fetched in cycle 1, in cycle 2 the instruction is decoded, and once again I am assuming that the branch is not taken, I am building the hardware to assume that the branch is not taken. However, by the end of that cycle I determine that the condition is in fact true. Unfortunately, the condition is true. So, the hardware, as soon as it detects this, has to squash this instruction. It has to squash instruction I plus 1, and subsequently in cycle 3 it has to start fetching from the correct target address. In other words, in cycle number 3 it has to fetch from whatever target address had been correctly computed in cycle number 2 ID stage, and subsequently the instruction which had been incorrectly fetched in the cycle number 2 will have to be ignored or annulled. Its activity should be cancelled, which I indicate by an X mark, suggesting that the instruction of which activity is happening in the ID stage at that point in time should be ignored, and any effects that it tries to produce should be negated by the hardware. And similarly, the instructions proceed through the pipeline as cancelled. So, we have this additional notation of an annulled or a cancelled instruction going through the pipeline. If there is a cancelled instruction going through the pipeline, it will not be allowed to modify the state of the processor, such as updating registers and so on. It merely, unfortunately, occupies a cycle. So, it amounts to one cycle in which no instruction is completed, but at least the correctness of the program is not compromised. Okay, so, the bottom line is that under the static not taken branch prediction policy, the hardware was built to automatically fetch the next instruction, assuming that the branch was not taken. And in situations where the hardware was wrong, some corrective action has to be taken, squashing the instruction and moving an annulled or cancelled instruction through the pipeline, as a consequence of which there is the equivalent of one branch stall cycle. So, we see that there are these two cases. In the first case, where the guess was correct, there were 0 stall cycles. In the second case, where the guess was wrong, there would be one stall cycle. Therefore, if 75% of the time, or being more optimistic, if 90% of the time I was correct in my guess, then 90% of the time there are 0 stall cycles, and only 1% or 10% of the time is there a stall cycle, and therefore the average control hazard problem will amount to 0.1 stall cycles rather than 1 stall cycles, if I look at the effect over an entire program. So, we have substantially reduced the impact if the rate of success of the guess is high. Right? But in general, we could say that the average branch penalty will be less than 1 cycle, and therefore this should be viewed as an improvement over the alternative, where there was guaranteed to be 1 stall cycle, where we refused to make a guess and just waited for 1 stall cycle without taking any action. Therefore, the idea of static branch prediction can lead to improved performance as far as the pipeline is concerned. It will lead to a little bit more complication in the pipeline, in that there must be built into the pipeline the capability of detecting that the condition was wrongly predicted, and that therefore an annulled instruction must be passed through the pipeline without updating the processor state. So, some complication in the design of the processor pipeline. But this is an idea which seems to make some sense in the light of reducing the performance on average. Improving the performance on average, reducing the number of stall cycles on average for a program. And there could be other static policies, but this is one example which seems to make good sense. Now, an additional idea which is often talked about in connection with control hazards is the idea of something called delayed branching. And the idea of delayed branching is that you actually design the hardware so that the control transfer takes place maybe after a few of the following instructions. As a simple example, let us suppose that I design the processor pipeline so that after the branch if equal to 0 instruction, the branch if equal to 0 instruction is going to transfer control to target if R1 is equal to R2. But if I design the hardware so that there was a property that the control transfer, even if R1 is equal to R2, the control transfer to the target address will take place only after the add instruction which follows the branch instruction is executed. Then by doing this, I am actually providing that one cycle in which I need not make a guess about whether the branch instruction is taken or not, because the add instruction has to be executed by definition. And therefore, I avoid the stall cycle entirely. There is no need to make a guess, there is no need to stall the processor for one pipeline. After the conditional branch instruction, we automatically execute the next instruction as per the definition of what a branch instruction means. And we have seen this idea before. When we were talking about interesting notes in the MIPS-1 instruction set architecture manual, this was the branch delay slot idea that we saw. The warning that we saw in the processor instruction set architecture manual was for control transfer instructions. The transfer of control takes place only following the instruction which immediately follows the control transfer instruction, which is the situation that we were seeing over here. The control transfer happens not after the branch instruction, but after the instruction following the branch instruction. Hence the name branch delay slot. So this idea we had seen, something that is used inside the MIPS-1 instruction set architecture, and we now understand why. It's being used to allow for the MIPS-1 processors to be designed using pipelines of the kind that we have seen, in which it's difficult to avoid one stall cycle. Okay, so with this delayed branching then, this is the idea, and we'll use the terminology of delay slot to refer to the instruction, in this case one instruction after the branch instruction that will be executed whether or not the branch is taken. Now the question that arises now is, it's well and good to talk about this property of the branch instruction, but from the perspective of the programmer or the compiler, this becomes a little bit of a problem. We have to actually write programs, so the compiler has to compile programs taking this into account. And the question then becomes a question of how does one fill the delay slot? There is a need to put something into the instruction slot following the branch instruction. How does one find a useful instruction to put there? That is the question which arises. Okay, now very clearly, the possible kinds of instructions which could be put into a delay slot are instructions that do not affect the branching condition, and therefore in some sense one has to be careful in deciding what instruction could go into the delay slot. Now this could be done by the compiler, or it might be something that the programmer does, but in either case let us view it from the perspective of the task being done by the compiler. The question then boils down to, from where will the compiler get instructions to put into the delay slots? Now there are a few possibilities. One possibility is that the compiler could take the first instruction from the branch target address. So we had the branch instruction and it's going to transfer control to some target if the condition is true. Therefore the idea here in the first suggestion is that the first instruction from the branch target could be brought and put into the delay slot. Another possibility is that the first instruction from the not taken path could be put into the delay slot. And the third possibility is that an instruction could be taken from somewhere before the branch instruction and put into the branch delay slot. One of the instructions preceding the branch instruction could be moved after the branch instruction. And in all cases, it would have to be carefully determined that the meaning of the program does not change. Now, the first idea, moving the first instruction from the branch target address into the branch delay slot, clearly will be a good thing to do for all cases where the branch is taken, because we know that if the branch is taken, then the instruction which is going to be executed after the branch is going to be the instruction at the branch target address, and therefore moving that instruction into the branch delay slot where it will be executed anyway is beneficial. By the same token, the second option of moving the first instruction from the fall through path, in other words the branch not taken path, will be valuable only if the branch is not taken. And the last option is one which would be useful whether or not the branch is taken, but the compiler must identify an instruction which can carefully be moved into the branch delay slot by checking the independence of instructions, the change in meaning of the program, etc. But let me just take one of the other two. I think what I'll do is I'll taking an instruction from the branch target address as an example, just to show that that may be generally useful despite the fact that it's of value only when the branch is taken. Okay, now let's think about the situation where we are going to fill the branch delay slot with the first instruction from the branch target. An alternative would have been to fill it with the first instruction from the fall through path. Now clearly what the compiler is going to have to do is it can move the instruction from the branch target to the branch delay slot, but in so doing it has to bear in mind that the instruction in the branch target, in the branch delay slot, is going to be executed whether or not the branch is taken. Therefore, if the branch is not taken and the first instruction from the branch target is executed, then some corrective action has to be taken, and therefore the compiler will have to do that corrective action by including some patch up code or corrective code, which will correct the meaning of the resultant program to be correct, to be as per the original program. Let's look at a very simple example of this. So the situation is I have a branch if equal to 0 R1 target instruction, and if I look at the target, I am showing you a label called target somewhere later in the program, where the instruction at the target address is add I R7 R7 and it is followed by some instructions. The next one is apparently a load word instruction. I am not showing you all the instructions in between, hence the ... Now the idea that we are going to look into is moving the add I instruction into the branch delay slot. Now the branch delay slot is the one immediately following the branch equal to 0 instruction. Now if I am to move the add I instruction into the branch delay slot, then I do have to worry about the fall through path. Therefore, I am going to show you a label which is the fall through label. So there is some instruction at the fall through path. Now if I move the add I instruction into the branch delay slot, then you will notice I am moving it. Therefore, the add I instruction is going to move up and the target address is going to get associated with the next instruction in the program. So I show the add I instruction moved up, and I show the target address is now associated with the load word instruction. Now we have to worry about the situation where the branch if equal to 0 instruction is executed and the condition is found to be false. If the condition is going to be found to be false, then we are actually going to transfer control to the fall through path, which is the next instruction in the program. And unfortunately, in the fall through path, the add I R7 R7 instruction should not have been executed. I had artificially caused it to be executed by moving the add I instruction from the target address into the branch delay slot. Therefore, the corrective action which I could take at this point is to undo the effect of that instruction, maybe by subtracting 1 from the register that had been incremented by the instruction which was moved into the branch delay slot. So this is an example of patch up code, a very simple example. But in general, the compiler would have to do the filling of the branch delay slot and the appropriate patching up of the program to ensure that the resultant program runs correctly regardless of whether branches are taken or not taken. The net result will be, of course, that in this particular example, every time the branch is taken, we get the benefit of the branch delay slot filled with an instruction that would have been executed anyway. However, in situations where the branch is not taken, we have 2 additional instructions that are executed that could have been avoided, and we have the equivalent of 2 cycles in which no useful instruction is being executed. Okay, now we should therefore note that the idea of filling the branch delay slot with an instruction from the target or from the fall through path may involve some patch up code, but depending on the program's behavior, in other words depending on the frequency of the branch being taken or not taken, this idea may still be beneficial for the improved execution of the program, and therefore it should not be ruled out of hand. Now it should also be borne in mind that the more the number of delay slots, the harder it will be to fill them usefully. And the reason that I point this out is that up to now we were assuming that associated with each branch instruction there was one branch delay slot that had to be filled. But we could have pipelines in which, because of the nature of the pipeline, there is a need to have 2 branch delay slots or 3 branch delay slots. In other words, after the branch, when the branch instruction is executed, it might not be the case that the condition and the target address can be resolved in the ID stage. It may be that it was not feasible to do that in a particular process or pipeline, and the result may be that there is a need for 2 or 3 or maybe even 4 branch delay slots, in which case that would be a warning to the programmer and the compiler in the instruction set architecture manual, for example, that there are 2 branch delay slots. And it then becomes the problem of the compiler every time it comes across a branch if equal to 0 instruction to find 2 instructions that can be filled in delay slots after the branch instruction. And the problem becomes harder and harder, in that it becomes necessary to find preferably 2 useful instructions, and if there are 3 branch delay slots, 3 useful instructions, and so on. Okay, we will continue from this point in the lecture that follows. Let me just remind you that in this lecture we have looked in some detail at the hazardous problem of control hazards, which arises from the execution of branch instructions, conditional branch instructions. And while many techniques are possible to reduce the impact of the branch instruction by complicating the earlier stages of the pipeline and make the resolution of the branch as early in the pipeline as possible, it may be the need, it may end up being necessary for the designers of the pipeline to pass the problem on to the compiler in the form of warnings in the instruction set architecture manual regarding when the effect of the branch will take place, and the compiler then has to worry about filling branch delay slots. We look a little bit more about this issue in the next lecture. Thank you.